Yeah, thank you. Thanks for inviting me. So yeah, this is a report on joint work with Qiu and Fabian Haiden. And this is from a paper from 2023, which we split into two parts because it was too long. So the first part appeared to, the first half now appeared today on the archive on the where the old paper was, and the second part will appear in the next days. But you can already find it on my webpage if you're curious. And so, right, today we'll talk about more of the second part, but which focuses on these relative graded Brauer algebras, but we'll also talk about some stuff from the first part. So, right, the first part of this talk will be about these relative graded Brauer algebras. We call them for short RGB algebras, which generalize usual Brauer algebras, and they are associated with a so-called mixed angulated surfaces. I'll try to explain that. And then we'll also look at the Koszul duals of these graded algebras or dg-algebras, which are then, which will be related with cyclic quotients of Ginzburg algebras. So that will be the first part. And then the second part, I'll say, I'll mention that there's a partial geometric model for these categories and how one gets from this to a space of stability conditions, to describing the space of stability conditions on these categories in terms of quadratic differentials. Right. So, and yeah, if there's any questions during the talk, feel free to interrupt me at any point. So, right, we consider weighted marked surfaces. Weighted marked surfaces with mixed angulations. So what exactly does this mean? I'll now give a long list of things which come about with this. So first of all, we have a surface, right? So S is a graded, and then the grading isn't actually on the surface, but it's on the complement of the marked points and other stuff. This is not so important. I won't go into this. So think of graded, and then it's compact, and it's oriented. This is the surface. And possibly it has possibly boundary, but it possibly with boundary. But boundary can also be empty. That's the first input. Then you have this surface carries decorations of multiple types. So the first type of decoration will be singular points. Singular points. And the singular points, they will be the centers of the polygons of the mixed angulation. Centers of polygons. So this is a bit abstract at this moment. We will see an example in a minute. So bear with me while I slowly unravel all the input data. So we have these singular points, and they are not only decorations of the surface. They can lie on the boundary and the interior, but they're also further decorated with a degree. So each the infinity degrees are reserved for the boundary singular points. So a singular point lies on the boundary if and only if its degree is infinite. Boundary. Let me write it like this. This is delta intersected the boundary of S. Then you have marked points, so M inside of S. These are a bit different to the marked points you may be used to from, say, cluster theory of marked surfaces. Because if there are singular points on the boundary, there will be infinitely many marked points on the boundary. Otherwise, marked points, if there's no singular points at all, then marked points can lie, there's only finitely many of them, and they can always lie in the interior of the boundary, and then it's maybe more what you're used to. So but this might be clear in the example in a minute. So these marked points, they are the vertices of the polygons. Right, and so if there's infinitely many marked points, that means we have infinite gods, actually, in the story, infinity gods. Then next, and or maybe finally, so what's now a mixed angulation? If you have this data, a mixed angulation is a decomposition of the surface into polygons such that each n-gon contains a unique singular point of degree n, singular point of degree n. So somehow, if we have a point, this will always be an interior point of an n-gon. The valence, the number of corners of the gons don't change if you look at the center points. If you have a fixed surface. And then one example, or one class of examples of this would be triangulations of marked surfaces, which is a fairly classical or fairly much better known or more, it appears in a different number of different circumstances setting. So in this, what does this correspond to? This corresponds to the case where all degrees are equal to 3. Degrees equal to 3. In particular, there are no boundary singular points because boundary singular points always have degree infinity. So in that case, it's really the same thing that you should know. You have finitely many marked points, and you look at triangulations or maybe ideal triangulations. And it's the story from, say, cluster theory of surfaces. And then a second example would be the following. So this is the disk. Now there's a lot to unravel here. So first of all, we have the singular points, which are drawn by thick green dots, right? There's 3 interior singular points, and let's say 4 on the boundary. One could have, of course, chosen differently, but this is the example. And then there are marked points. These are drawn in orange, and I can't draw all of them because there will be infinitely many of them. And the way this works is that there are a few marked points here and there, they're discrete. And then whenever you approach a singular point, they become dense. So if you look, for instance, here near this singular point at the bottom left of degree infinite, there's a lot of marked points. And the closer you get, the shorter the distance will be, and they will converge to this point. And but it's countably many, but dense near the singular point. And then you have these are just the decorations, the marked points and the singular points. And then we have the mixed angulation. This is drawn in blue. So there's also the S graph, which is in yellow. We'll have that in a moment. I'll say what the S graph is in a moment. But let's look at the example so far. Ready? So the mixed angulation, this is in blue, and it cuts the surface into polygons. And if you check, so for instance here, you have a 3-gon where you have 2 blue edges, and you also count this boundary edge connecting 2 marked points. So this means the singular point here is decorated by 3. Now, say we were to change it, to change the surface by adding a marked point here, then this integer would change from 3 to 4, because then suddenly it's it is the center of a 4-gon and not a 3-gon anymore. So the upshot is that the degrees of the singular points is exactly in which n-gon there are. So if you look at the singular point on the boundary, you will have an infinite gon, right? Because there's infinitely many marked points in this polygon here. So it's really an infinitygon, and the singular point lies in the infinitygon. Okay, right. So yeah, it's a fairly general class of surfaces with decorations, which we are considering here. And right. Now next, I'll tell you what the S graph is of a mixed angulation. So dual to the mixed angulation is the S graph, which I'll write by an S with a thing. And what is this? So this is a ribbon graph. Ribbon graph together together with data of integers, integer d of hi plus 1 bigger or equal than 1 for each pair of consecutive half edges. Consecutive half edges. Such that if you look at a single vertex and you look at the half edges hi incident to a vertex v, and you sum these distances of these half edges, hi plus 1, then you're exactly supposed to get the degree of the vertex. So if we look at an example, if this is your S graph, and the degree of the vertex is, say, we're in degree 5, then you could have here, this distance could be 2, this distance could also be 2, and this could be 1. And then the sum of these 3 is 5. Or you could also say this is 1 and this is 3. That would also be possible. But all of them need to be bigger or equal than 1. So if we go back to the, if we go back to this example on the left, the S graph here is the dual graph to the mixed angulation. This is drawn in yellow. And let's maybe also find the degrees. So this degree here, it is 1. And this degree here will be 3. Because the way you get the degree is by looking how many, how do you say this? So you could, there's boundary edges which are skipped, basically. And every boundary edge which is skipped tells you that you have to add 1 to the degree. So the degree here is 1. No, it's actually 2. Here it is 1, and here it is 1, and here it is 1. Anyway, the degrees are not so important. They're basically some grading information. More important is that you have this graph, and it is dual to the mixed angulation, and it encodes the mixed angulation together with these degrees. And you need these infinitely many marked points to somehow record all the possible positions of the endpoints of the S graph. Right. So yeah, this is a bit. This is somehow the input of a mixed angulated surface together with an S graph. And if there's no questions about it, I'll next define the corresponding relative graded Brauer graph algebra. Sorry, I said something wrong. The endpoints of the S graph are the singular points, not the marked points. The marked points are the endpoints of the mixed angulation. And because there's only finitely many singular points, to record all possible mixed angulations, you need the extra datum of the degrees, so that the datum of a mixed angulation is equivalent to the datum of an S graph. Anyway, maybe not the most important detail. So now, to define the RGB algebra, the graded Brauer graph algebra, we need to input an n bigger than 0, an integer which is a common multiple. So we first fix an S graph, which is dual to mixed angulation. Then you choose an n, which is a common multiple of the degrees of the vertices. which are just the singular points of S, by which of course I only mean the finite ones. If there's infinite vertices of degree infinite, infinity, this is not, you don't have to, it doesn't, anything is a multiple of infinity. Okay, and then the relative graded Brauer graph algebra. And we shorten this by RGB algebra. We denote this by ASN. So it takes as input the S graph and an integer n. This is obtained as follows. So first of all, it's we define it from a quiver. And so this quiver has vertices. And the vertices of the underlying quiver are simply the edges of the S graph. Right. Then next, we want to know the arrows of the quiver. So there are two types of arrows. First of all, if you have an interior vertex, then this would be your the S graph is in yellow. The nodes of the quiver are in what is that, magenta, and then you have an arrow like this, A. So if this is HI and this is HI plus 1, you have an arrow AI, and the degree of AI is equal to the distance of HI and HI plus 1. So it's indeed a grading information. And we're in the cohomological grading convention here. So it's in positive degrees, so it's non-connective. Right, so that's the first type of arrows. Whenever you have two consecutive half edges, you get an arrow. The second type happens if you're on the boundary and you have a half edge which connects to a boundary vertex. If that is the case, you add a loop tau, and the degree of tau is always n minus 1. So it's a quiver coming from the S graph plus additional loops at the boundary. Now, okay, we have vertices, we have arrows. Next, we'll define relations, and finally, we'll define a differential. So next, we need relations, and there will be 4 types of relations. So yeah, the definition is slightly involved. Okay, but we'll get through it. If you know Brauer graph algebras, you'll understand at least half of the definition. So let's say we have an arrangement like that. Yeah, I'll explain the relation with the Brauer graph algebras a bit later. So this is our S graph. Then this is our quiver, right? Locally, the quiver looks like that. And then what you have here is, maybe this is actually relation 2. I'll tell you relation 1 in a minute. So here you have a cycle going around this. So cycle C. And if you go around like this, you get a cycle C prime, right? Which is just, C prime is just this cycle. Then I want that, and let's say this node here of the S graph has degree, here we have degree m, and here we have degree m prime. Then the relation is that C to the n divided by m is equal to C prime divided by n divided to the power of n divided by m prime. So this is the relation. Right, this is relation 2 because there's a different relation I wanted to tell you first about. So relation 1 is that, which is a bit simpler to explain. If we copy paste this picture, there's a different relation, not about the 2 loops, but it's about a certain composition. Namely, this composition here and this composition here, they vanish. Composite. So basically, if you have two different vertices, and then the arrows coming from the two different vertices, they just compose to zero. This is your relation. Right. So, right, these are the two types of relations, and these are Brauer graph algebra type relations. Brauer graph algebra type relations. So they're very, very similar. Actually, they're just a graded analog of the relations you have in a Brauer graph algebra. But then there's additional relations coming from the boundary. Yeah, if you have singular points on the boundary. So what are these? There's two more. The first one is not so hard. Any tau squared is 0. So any loop coming from a boundary edge squares to 0. And then let's say you have an arrangement like this. You have a boundary component with a singular point, and then you have two edges coming out. Then you get, as before, you get an arrow here, and then you also have these loops. So you have tau1, you have an arrow A, and you have tau2. And then the relation is that A tau1 is equal to -1 to the degree of A tau 2A. Yeah. So the loops and the arrows commute when it makes sense to ask if they commute up to, in a graded sense. Right. And then I'll tell you a little bit how you should think about this in 1 second. The final thing, which is very easy to say, is the differential. Because there's only one type of generator who has non-trivial differential. If you have a boundary component like this, and here you have your cycle C, and here you have tau, then the differential of tau, the differential raises the degree by 1. This it will be c to the n divided by m, where this has degree m. If you go once around, you get a degree m arrow. If you take it to the power n divided by m, you get a degree n arrow cycle. So like this, just going once around gives you a degree m thing, and then going n divided by m times around gives you a degree n thing. And this is exactly the degree of the differential of tau, because tau had degree n-1, and we're in the cohomological grading convention where the degree raises by 1 if you take the differential. Okay, so this is the full definition, and then the upshot is the following. So away from the boundary, this is simply a graded version of a Brauer graph algebra. So Brauer graph algebras, they're really honest algebras. They live in degree 0. But then you can put gradings on the arrows, and then you would come up with a notion like this, where there's no singular points. But then if you have singular points, something interesting happens, namely at boundary singular points, point of valency n, this relative graded Brauer graph algebra, and so this is the relative part, right? The graded is clear where it comes from. Relative, by relative we mean it has somehow information about the boundary, and this relative part is the stuff lying at the singular points, boundary singular points. And in this case, it is described by, well, let me say it informally. It's the path algebra of an AN cover tensored with an n-1 spherical object. Spherical object. Right? Where does the spherical object come from? Basically, if you take k plus tau k, tau squares to 0, this gives you the endomorphism algebra of a spherical object. An n-1 spherical object. And right, concretely, let me go to the next page. The algebra is if you're on a boundary component like this, then your algebra looks like this: 1, 2, 3, and so on. You have arrows A1, A2, A3, tau 1, tau 2, tau 3, and so on. And then the AI and tau I graded commute. So it's really an AN curve. This gives you the A arrows, and then tensor it with this spherical object, which is whose endomorphisms, the non-identity part, give you this tau, and then because you're taking a tensor product, things graded commute. So yeah, you can maybe even make this precise. Right, and then this is somehow how you should think about these algebras, and then the proposition. Or maybe one fun fact about this, that this algebra ASN is the RGB algebra. GB algebra, in case you already forgot the notation. This is n Calabi-Yau. So let's say right n Calabi-Yau, maybe weekly. If no if there are no boundary singular points, and S satisfies an orientation assumption. An orientation assumption. This orientation assumption is automatic. It's a bit technical. It's automatic if n is odd. So I don't want to explain it here. And then so why can it not be Calabi-Yau in the case of boundary singular points? The expectation is that in the presence of boundary singular points, that this RGB algebra is relative right Calabi-Yau, relative right and Calabi-Yau. But we didn't manage to prove this. Right. So this is some
with
basically
respect to relative with respect to what?
Yes, excellent question. I'm not sure. I don't think I'll give the functor in this talk. So there's if you restrict to the boundary, basically, I mean, this is not exactly what you want to do. You want to, so if you restrict to the boundary, you would restrict to these AN quavers, and then each AN quaver you have to restrict to, well, there's n+1 maps from the AN quaver to K, which are given by basically evaluating at the final point, at the beginning point, and taking the cones of all the maps. And this gives you n+1 maps from the AN quaver to the field. And if you combine basically this, so from the RGB algebra, you would first restrict to the AN quavers and then restrict with these n+1 maps. This would give you the Calabi-Yau functor. Yeah.
Thank you.
But, yeah, thanks for the question.
But could I ask also about this?
Yeah.
And what this is? So C is a cycle of some length.
You mean here on the left, or?
Yeah, on the left page, yeah.
Right. So that I'm saying the differential of the generator tau is -1 to the n, sorry, times the cycle to a power. So yeah, C is a cycle. C is this cycle where I just go once around. I start here and end here. Okay. This gives me an endomorphism. This gives me an element on the path algebra of the quiver.
I see.
And then I'm setting the differential of this part in the path algebra of I'm defining a dg-algebra by specifying the differential on the generators. The differential on generators is 0 except for the taus, and the differential of the tau is the power of this cycle, which ends at the same node as it lives.
Okay, yeah, thanks.
Yeah. Any other questions while we're having a small break?
I was wondering, is there like a symplectic model for this behind this, or?
Yes, so this will be right. Very good question. So as I explain next, when you go to the Koszul dual algebra, you get a cyclic quotient of a relative Ginzburg algebra. And this relative Ginzburg algebra is expected to describe a partially wrapped Fukaya category of a Calabi-Yau threefold. So what you would expect is that this describes some kind of equivariant Fukaya category. So I don't think there's an exact symplectic. I wouldn't know how to. Basically, the question: does the cyclic quotient of a Fukaya category again describe a Fukaya category? I'm not so sure if this is realistic, but at least it's a group quotient of something which comes conjecturally from a Fukaya category. Of something n-dimensional, right? So if you're in Calabi-Yau dimension n, it's a n-dimensional symplectic thing.
Yeah, I see.
Yes.
Okay, but there's no interpretation for surface in particular.
Well, it's the Fukaya category of the surface with coefficients in a certain co-sheaf of categories.
Okay.
That would be the, yeah. I mean, it's not, Fukaya categories of surfaces are not n Calabi-Yau. They are relative one Calabi-Yau. Yeah.
Okay, thanks.
Thanks for the question. Yeah. Any more questions? Since that's not the case, let's continue with the Koszul dual dg-algebra. This is denoted by GSN. So there's a bit of a question of, which direction does Koszul duality go? Because Koszul duality is not exactly an involution. It's an involution up to completion. So we want that A as n is the Koszul dual of this right? It's somehow an inverse image of the Koszul dual, not the image under Koszul duality. And so what is it roughly? I'll first give like a rough explanation of what it is, and then I'll give a slightly more precise cool description of it in terms of limits or colimits. So first of all, it's a connective, meaning concentrated in negative degrees. Negative degrees, dg-algebra. And it's at a it again, like similar to the RGB algebra, you can somehow think of it as having a description at boundary vertices and having a description in the internal part. And at boundary vertices, it's described by first of all, you take the path algebra of an AN curve, and then you tensor it. So under Koszul duality, in a derived sense, the AN curve doesn't really change much. So you take a polynomial algebra where the generator is in degree 2 minus n. And if you take the Koszul dual of this is exactly an n-1 spherical object. Right? So basically, what happens at the boundary vertices is that you're just taking the Koszul dual, and this commutes with the tensor product, or changes the tensor product by only going to the Koszul dual of the spherical object, and that is a polynomial algebra. And then the second or this next point is a bit more interesting and non-trivial. So add a degree m vertex of degree m, sorry, of valency n. It's described. It is described by a z modulo n divided by mz quotient of the relative Ginzburg algebra of an n-gon. So let me explain that in an example. So if you're, let's say n is equal to 3 and m is equal to 1, then, well, let's say we look at a triangle. And what is the quiver of a triangle? Well, you just have three, the arrows of the direction of the arrows now changed. Before they were going counterclockwise, now they're going clockwise. And I think that's deliberate. So if you have a triangle, what is the relative Ginzburg algebra of this quiver? Let's call it ABC. With potential W is CBA. Then the relative Ginzburg algebra this comes from a graded quiver with 3 vertices and 6 arrows. Basically, you take the double of every arrow. So you take B and B star, A and A star, and C and C star. And then the degree of A is equal to 0. The degree of A star is equal to 1. Sorry, minus 1. Similarly, the degree of B is 0, and so on. And this algebra, the triangle has this Z modulo 3Z symmetry, which just corresponds to rotating it. And this algebra has the same symmetry. This quiver has the same symmetry. So you can pass to the Z modulo 3Z quotient. And then what do you get? Well, you get a single vertex with 2 loops, A and A star, with the degree of A and A star is above, and the differential of A star is A squared. Here also above, the differential of A star was CB. And so this gives you an like the Koszul dual is always given by going to a quotient, a cyclic quotient of such relative Ginzburg algebra, which in the simplest case of a triangle looks like that. Otherwise, it's a bit more elaborate and complicated to describe, but it's somehow fairly concrete. And it's interesting that there's a relation between these generalizations of Brauer graph algebras and generalizations of Ginzburg algebras via Koszul duality. Now, this was a very rough description of the Koszul dual. Let me make a slightly more precise statement. So the finitely so the DG category version of TSN with objects, the vertices. So if you have a quiver algebra, you can always consider this as a DG category with finitely many objects, where every vertex is an object. This doesn't hurt. And it's Morita equivalent, and it's kind of, for technical reasons, it's better to do this in this case. So this DG category, this is the homotopy colimit. Of a diagram of DG categories. Of the diagram. Which which associates to each edge an edge of the S graph. It associates this thing here, the DG category with a single object and a freely generated loop, which is just the polynomial algebra. It associates to a vertex. It is so either the cyclic quotient of a relative Ginzburg algebra / DG category with finitely many objects, or again this AN quiver tensored with this Laurent algebra, and then to each incidence of V and E. This is some dg functor. Let me just tell you in an example. For n is equal to 3 and m is equal to 1, you have kt minus 1 going to this algebra we have on the left, a star, and this would map t minus 1 to a star, a minus a star. This is a degree minus 1 element of the path algebra. Its differential is 0, as you can easily compute. This gives you a well-defined dg functor between two dg categories, in this case with a single object. And the point is, these rules above, they define you an entire diagram of dg categories. And if you now take the homotopy colimit of this diagram in the category of dg categories, then you get this dg category GSN. This should be a bold N. Okay. So some remarks are in order. So first of all, for n is equal to 3, and no boundary singular points. No boundary singular points. The Jacobian algebra, H0 of I guess in cohomological grading, GSN, is gentle and was considered or appears in work of Labadini, Fragoso, and Mu. On surfaces with z modulo 3z surfaces with z modulo 3z orbifold points. And then second remark, second of 3, the above diagram, with colimit GSN, or rather homotopy colimit, defines a co-sheaf of dg categories. A co-sheaf of dg categories on the S-graph. In fact, this is even a perverse Schober, so a categorified perverse sheaf. If you've been following my earlier work, this kind of in the back and used a lot in the 2 papers, this theory. But the point is, it's a co-sheaf of categories, and the Foucault category of surface also arises as the global sections of a co-sheaf of categories on the dual graph. And in this setting, this is somehow the Foucault category of the surface with coefficients in a more general co-sheaf. I think that's a very productive way of thinking about it. As a generalization of the Foucault category of a surface, just with different coefficients, just like imagining singular homology with coefficient, well, it's not singular, sheaf cohomology with coefficients in a different sheaf. All right, going back to Severin's earlier question. And then third remark, there's also an A infinity perspective on this graded Brauer of algebra. So ASN also describes the endomorphism algebra. So ASN was the RGB algebra, the endomorphism algebra of an arc system in an A infinity deformation. The formation over the formal polynomials. Not Laurent, just normal polynomials. I guess I said Laurent earlier, that was wrong. Of the topological Foucault category. So that's a different way to connect it with the topological Foucault category of the surface. Category of a marked surface. So yeah, it's an A infinity deformation of say of a Gentile algebra or graded Gentile algebra in a derived sense. And concretely, we explain this in the context of or in the language of A infinity categories, since there it's a good way to talk about deformation theory or deformations maybe. So right, that explains, or that gives everything I wanted to tell you purely about RGB algebras and the relation with the Koszul dual. You can now ask again questions before I switch topics slightly.
Maybe I can ask a question again. So this deformation here is of a graded base, right? Your T
yes.
minus n have some degree, right? Okay. And the other thing I wanted to ask is this condition that it is a Purvis-Schober. Is that something that is difficult to check, or is it sort of not so difficult?
It's non-trivial, definitely. I mean, somehow, so you know that it's the non-trivial thing to check, I think, or so there's two things. Or how do we check this? We know that the relative Ginzburg algebra of an n-gon describes a Purvis-Schober on an n-gon. There are some conditions on the co-sheaf, local conditions to be a Purvis-Schober. And then checking it there it's non-trivial, but it has been done in my earlier work. And then using that, the fact that this locally it's a homotopy limit and homotopy co-limit of the cyclic group action, you can use that to deduce that it's also a Purvis-Schober when you pass to the cyclic quotient.
I see.
That's again a slightly non-trivial argument, but it's not super hard. But there is something you have to check.
All right, thanks.
Yeah, thanks for the question. Okay, then we're now in part 2, which is about partial geometric models and stability conditions. And so let me just wave my hands and say that there's a general sheaf theory approach, or maybe you could also call this a local to global construction. Global construction, which produces, or which allows you to associate an object A gamma with each graded arc gamma in the surface with endpoints at the singular points. So a graded arc means, well, let's forget about the grading. An arc is just an embedded curve. And then if you look at the collection of arcs, A gamma, where gamma is an edge of the S graph, this gives you exactly the set of projectives of this relative graded Brauer graph algebra coming from the vertices. Right, every vertex of a curva algebra has an associated projective and direct summand of this algebra, and they exactly correspond in terms of this geometric description. Every edge of the S graph itself is a curve, and this curve corresponds to the projective. Right. Are there any questions?
Sorry, so the local to global construction in this case gives you the category of modules over ASN? Is that you? I mean, you didn't state it explicitly, but
so dperf of ASN. This is a full subcategory of dfin of GSN, which is the full subcategory of dperf of GSN. In general, none of these inclusions are equivalences. This is never an equivalence. This is sometimes an equivalence, the first one. And then this last thing here has a sheaf model. Actually, both of them have a sheaf model. Sheaf. And so, but then you can check actually that you can check that in using the sheaf model that the things you produce, it lies in the full subcategory.
Mm-hmm. So, so the sheaf model is the Purvis-Schober which you alluded to.
Yes. I mean, this diagram of DG categories, it gives you the co-sheaf, If you then pass to the derived categories and to the adjoint functors, you get a sheaf, which is your perfect Schober.
Yes, thank you. Yes.
Thanks for the question. Sorry. Okay. Now, okay, we can realize every arc as an object, and the edges of the S graph are themselves arcs, and they give you the projectives. And maybe theorem. This collection A gamma, where gamma is an edge of the S graph, forms a simple-minded collection. A generating simple-minded collection of d perf of the graded Brauer algebra, relative graded Brauer algebra. To what the question before, just one comment. So the point of this Koszul duality is that the Brauer algebras themselves, they don't glue so well, but once you pass to the Koszul duals, they glue very well in the sense of there being a sheaf. But there is, in general, no sheaf for the Brauer algebras only. So yeah, sheaf theory and Koszul duality do not commute. And the fact that they do not commute is very crucial for our constructions to work. Okay. Okay, so A gamma forms a generating simple-minded collection, hence is the set of simples in a finite length hard, of a bounded T structure. This is maybe where we make our first touch with stability conditions, because stability conditions are about T structures. Right, every S graph gives you a finite length hard. And then what happens if you change the S graph? So flipping the S graph at an edge E to a new S graph S prime, there's an associated equivalence. And from d perf of A S n to d perf of A S prime n. And the change in hard corresponds to simple tilting. Change in hard corresponds to simple tilting. At AE. So if you have a simple-minded collection, you can tilt any of these simple objects in the simple-minded collection and get a new simple-minded collection. Well, I guess there are some conditions you need to have satisfied, but they are satisfied here. So in this setting, you can tilt any simple-minded collection, get a new T structure, which again has a simple-minded collection. And the way why did we introduce these complicated S graphs and mixed angulations and everything? This is so that you then exactly have a correspondence now between these combinatorial geometric notions and the tilting theory. Simple tilts correspond, simple tilts of the simple-minded collection in this category correspond exactly to flips of the S graph, which in turn correspond exactly to flips of the mixed angulation. So this gives you a very nice geometric interpretation of the simple tilting theory of this class of n-Calabi-Yau or relative n-Calabi-Yau DG category, DG categories. So there's an somewhere I hid an example, maybe here. Yes. Right. So I don't have too much time. Yes. So let me reveal the example immediately. So here you see this is now. Let me try to take them to the other side. These are two surfaces, and It's actually one surface. Sorry, it is one surface with two different S graphs. Oh, what happened here? With two different S graphs. And what they changed, what I changed was I flipped them. So okay, so the change from here to here is a flip. Which edge did we flip? Well, I think it was this one. Right, if you flip this edge of the mixed angulation slash this edge of the S right, slash this edge of the S graph, right? You can either flip an edge of the mixed angulation or flip an edge of the S graph. It's all the same. Then you get a new S graph, right? And this is how it looks like basically. And this then the yellow stuff. So S graph stands for simple graph. The S graph encodes the simple objects in the heart, and the change in the S graph records you with the tilting of these simple objects. Right. So it's a. I think it's a very concrete and nice understanding of the tilting theory in this case. And then maybe one corollary of this is that there's an injection. Injection from the exchange graph of S graphs of the surface to the exchange graph of finite length hearts of the perfect derived category of ASN. So change graph of S graphs to the exchange graph. So what is the exchange graph of finite length hearts? So this is just a non-directed quiver, right? So the nodes of this graph would be the S graphs or the finite length hearts, and the connections between the nodes would be given by flips slash tilts. So whenever I tilt a finite length heart, I would connect to nodes in this graph, and then the corollary is that this one graph is a subgraph of the other graph. It's actually a connected component even, or a union of connected components. And because this exchange graph of graphs of S is the skeleton of a space of the space of framed quadratic differentials, framed quadratic differentials, you get the following other corollary from the above, namely that there is a map from the space of framed quadratic differentials of the surface to the space of stability conditions, of Bridgeland stability conditions on this perfect derived category. Which is this is framed quadratic differentials, which is a biholomorphism onto a union of connected components. And let's see how the time is. Yeah, my time is up. So let me just say about these frame quadratic differentials, they would be as in HKK. So they have poles of arbitrary order. They have zeros of different orders. And they also have exponential singularities. And so whatever type of quadratic differential you want to realize, you will be able to find some kinds of surfaces and suitable integer n, such that the stability conditions on the corresponding RGB algebra correspond to this class of quadratic differentials on the surface with a prescribed different types of singularities. So saying I want quadratic differentials with different singularities, say if you want more exponential singularities, you have to add more singular points on the boundary, and then basically every choice of input in the surface corresponded to a different type of restriction on the kinds of quadratic differentials you want to look at. Right. Okay. Yeah, that's all I think I have time to say. So, or maybe also wanted to say. So yeah, thanks for listening.
Yeah, great. Thank you very much. Are there any questions from the audience?
After Sibylle, after you, Sibylle.
Oh, okay. Yeah. So I have a question. So I suppose in the case where this ASN is a Brauer graph algebra, then these flips, I suppose, they correspond exactly to these. I guess Valentin Soto and we sometimes call them Kauer moves. They go back to a paper by Kauer from 1989, I think, or something, or 98 maybe. Yeah, 98. Is that right?
I suppose so. I wouldn't know perfectly well if that's correct, but that seemed very plausible. Well, I have to mention that we restrict to positive n, right? We don't do the case n is equal to 0.
Oh, okay, I see.
So it would be the analog of these moves in the positive case.
I see. Okay, so you don't do the 0. But wait, when you say positive n, that means what?
N bigger 0.
Okay.
Yeah,
but I mean,
Calabi-Yau dimension.
n in this
the
case.
Calabi-Yau dimension.
Oh, the Calabi-Yau dimension.
yeah,
Okay.
Brauer algebras are always 0 Calabi-Yau. They're symmetric.
Okay.
Right?
Yeah. Okay. I see. Okay. Cool. Okay. Great. Thanks.
About that, I think this Koszul, Professor Schober story and Koszul duality, that should also work for n is equal to 0 and n is negative. We haven't done it because it would be extra work, and then you don't. It's not so clear what the connection with stability conditions is.
I see.
But except for the stability conditions, everything should also have an analog for other choices.
Okay.
Yeah.
And if I may, I have a second question.
Please.
Okay, so this student of Claire Amiot's, Valentin Soto, she recently defined sort of generalized flips where instead of just like, for example, here in your S graph, you move just one side of the edge. She moves, if you have several edges connected, she moves them on both sides, like a flip of several edges. And it's not a consecutive thing of moving a single edge, and I wonder how that could, or if that can even fit into this injection of some sort of generalized exchange graph.
Good question. Is this the paper where she considers not relative or not graded Brauer graph algebras, or maybe Brauer graph algebras, but maybe a type of Brauer graph algebras which has this Q gentle component?
I mean, I don't exactly know in which paper it is.
Right. So she has this word. So
no, I think
examples of Brauer graph algebras come from
move. So in whichever paper she defines them, but I think there might be some other papers which.
But is it about Brauer graph algebras or it is about?
It's about Brauer graph algebras.
Ah, I see. Okay.
So basically, if you have several things, I mean, somehow in this, I mean, if you flip a blue edge,
yes,
then that means the yellow one sort of moves both endpoints to the thing, and somehow you can do that with several edges at once, and and yeah, I don't know. I thought it was kind of interesting because maybe one gets a little bit of a larger part of the exchange graph.
What do you mean larger part?
Well, of the exchange graph on the right, where you sort of look at the derived equivalences of the equivalences in the perfect derived category.
But I mean, the problem with not realizing everything on the right is that you only reflect finite length hearts in this tilting. Right, so it's not, the question is how can you describe the non-finite length hearts in a similar way? And that's probably, I mean, it's probably not true because they will have there will be hearts which are not finite length, and then there's the heart is, I mean, if you think of this example of the Kronecker quiver, and so in the first part of these two papers, we consider more general types of sheaves of categories, and usual topological Fukaya categories, meaning graded Gentile algebras, also fit in this framework. So then the Kronecker curve is an example, and there you have the geometric heart, which has lots of stable objects or semi-stable objects. And then it's somehow less clear how you would ever describe this in terms of this combinatorics.
I see.
And so I think that's kind of the problem with the real. I mean, I'm not with this injection not being well. I guess this injection is actually fine. I guess the expectation is that it's even a bijection, but you will never get
the bijection.
This one here, if I'm not mistaken. This is on YouTube. Very good.
Oh, really? It's not in the zero case, but
why? So well, I might be very confused then if you're saying.
Okay.
But let me see. I mean, what would not be in the image?
I don't have an example at hand, but I believe, for example, there might be a paper by Alexandra Zvonareva where she gives an example of things that are not given in this way. I mean, I don't know in the graded case,
Okay.
and when n is different from 0, maybe things behave slightly differently.
I mean, one thing which happens is that you can have different connected components. There will be different S-graphs which are not related by chains of flips. This can happen. Sasha also told me about the counterexample in that context. But then, right, maybe that's also related with these moves. I don't know.
Okay, I don't know. Okay, but thank you very much.
Yeah.
Dana, sorry.
Yeah, thanks. Sorry, I can't answer perfectly. I don't know.
Just a very basic question. Oh, yeah, all the hearts which you get are nearby with respect to the initial heart?
The initial. What exactly do you mean by this? What
I mean,
what do you mean by get?
Which you get by flipping. I mean,
Right. Yes.
you start with some S graph, and then that gives you some initial.
Sorry,
heart.
I'm not
No?
I'm not super familiar. Nearby means that it's between the heart and the shift of the heart.
The corresponding ale is between the ale and the shift of the ale, right?
I don't think that is true. I think you can just also shift everything. That is entirely possible.
I see.
Yes.
But flipping is an involution, or if you do it twice, then you actually
well, there
shift.
are grading informations, right?
I see. So flipping is not just So flipping is not an involution.
Right. Yeah. Right. I would have to check honestly. Like it's hard. But yeah. I mean,
Okay.
I wonder if is this contained in the grading information or not. I hope so. But yeah, I would have to check. Yeah.
Yes. Yeah. I'm just asking because in the cluster context, this is what you do. Yes.
Yeah. No, I don't think flipping is an involution. Wait. Flipping. Yeah, flipping twice is not. No.
No. So it's not.
Yeah.
I see.
Yeah.
I see.
It's also already not true for, say, just normal relative Ginzburg algebras or even non-relative Ginzburg algebras of surfaces.
Thank you very much.
Yeah, thanks for the questions.
Right. So I think Xiaofa Chen posted the link to the paper that you were talking about by Valentina Soto.
Oh, thank you. Oh, thank you very much.
Yes. Yeah, she considers both Brauer graph algebras and skew Brauer graph algebras, but it's two different theorems.
Okay. Well, if there are no further questions, then thanks, Merlin, again for the very nice talk.
Yeah, thank you very much. Very nice talk.